Mr. True, in this calculus video, we are going to look at question number 3 from the 2018 Calculus AP free response. This would be on the AB test and more than likely on the BC test as well, but I'm not positive about that, but it is an AB question. We have the graph of the continuous function g, which is right here in orange, which is the derivative of the function f, is shown. The function g is a piecewise function for the closed interval from -5 to 3, and then g of x takes on another type of function. Basically, it's still part of a piecewise function, but as opposed to being a linear piecewise function, we go into a parabola opening up for the closed interval from 3 to 6. And given the fact that f of 1 is equal to 3, what is the value of f of -5? Now, one thing you want to be aware of in this particular question, or others like it, anytime they give you a graph and tell you that it is a derivative, basically, of another function, you want to put that somewhere in your work that make the connection that, well, if g is the derivative of function f, then put it somewhere that you realize, okay, f prime is equal to g. That's going to help, and it's also going to be sort of a check for conditions check on another part of your question. Also, with your free response questions, anytime they give you a closed interval, start thinking in the back of your mind, I might somewhere within this problem need to work with the extreme value theorem, the intermediate value theorem, or the mean value theorem, which is actually not part of any 4 parts of this question, but it is something good to keep in mind. Now, another thing to remember is, I say this all the time in my classes, when you integrate a rate of change, you get an amount of change. So when they give you some kind of initial condition, f of 1 is equal to 3, and then they're asking you to find the value of this function somewhere else, that you're going to be accumulating as you integrate this function g, which is really just f prime, as you integrate the derivative of f, the rate of change of f, you're going to get an amount of change. So I like to say, okay, when you have an initial value and you want a value somewhere else you're going to find based off of your work with integration, that you want to say, okay, f of -5 is equal to, and start with your location where you have the initial value, which is going to be f of 1. And now off of that, you're going to add the amount of change you get from the integration, because again, when you integrate a rate of change, when you integrate f prime or g, you're going to find the amount of change in f. And you always want to set up your definite integral. Well, this is just how I teach. It's really not an absolute rule, but I like to set up my definite integrals starting off from that known value, which is 1. And then from that known value, it's just like thinking of, asking Apple Maps or Google Maps or whatever, map you're using, how do I get to somewhere from here? Well, the first thing it's going to identify is, where are you now? And then we'll tell you where you are at the x value of -5. And, well, you're going to be integrating f prime of x, or g of x, dx. Now, a couple of things here. I have the specific value of 5. If I were to change this independent variable to x and have my upper limit be the variable of x off of our initial condition value of 1, then you would have what is known as an accumulation function. An accumulation function which is going to tell you the value of this function at any unknown particular value of x. But now we're going to use the value of x, which is -5. Okay, well, you can't do definite integration in a standard way unless that lower limit is actually a lower limit. So I put my lower limit as 1 because my initial value, my initial known value, is at x equals 1. Well, we want to flip these limits around so that the lower limit is actually the lower limit. Well, when you swap the limits of definite integration, you're going to change this addition to subtraction. Okay, so now here we go. F of 1 starts off and is equal to 3. Now we're going to subtract the area that we accumulate in this graph, which is g or f prime, from negative 5 to 1. Okay, well our area from negative 5 to, basically we're looking at negative 2. Scales on this would have been nice. Okay, that's better. We're going to, in this problem, fall back on a couple of things we learned in calculus. One, how to estimate area or find a definite integral that involves common geometric regions, and then we're actually going to use integration with our parabola at some point. So from negative 5 to 1, well, we have a rectangle which has area below the x-axis. So I have a little spacer here because I didn't want to cut too much in my work area. And the width of that rectangle is going from negative 5 to negative 2. So we're looking at a length of 3 times its height, which is a height of 3. But this quote-unquote area that we're accumulating, or the definite integral which we're evaluating, the function is below the x-axis, giving you negative y values. So this is going to be 3 times negative 3. And that's going to be the area of our rectangle. Or I'm using the word area loosely. The negative is indicating that this is below the x-axis. Now, we have another rectangle here, which is going to give us some negative value for our definite integral. It's going to be the area of a triangle is 1/2 our base, which is from negative 2 to negative 1, a length of 1, times our height, which again, our function is bringing or taking on negative y values. So we're looking at a height of negative 3. And then from negative 1 to 0, our function is straight along the x-axis, so it's not accumulating any area at all. And we're going to 1. So now we have another area of this triangle here, which is going to have us an area 1/2 base, which is 1, times height, which is 2. And this is going to be 3 minus negative 9 minus 3 over 2 plus 1. And we're looking at 3 minus negative 18 over 2 minus 3 over 2 plus 2 over 2, which is going to give us 6 over 2 minus negative 18, negative 21, right? And now it's negative 19 over 2. We're subtracting that negative, so we should be looking at 25 over 2. Check my work here. Boom. That is our correct answer. Now on the AP test, this is a 2-point question for this part of the free response question. You got a point for the proper integral written out with our incorrect lower and upper limits, and of course starting off with our f of 1, and we get a point for our final answer. Moving on to part 2 right now. Part B, we want to evaluate the definite integral of g of x dx from the value of 1 to 6. So as we look over here, we want to evaluate the area we're accumulating, or the value of the definite integral. Some teachers have a problem with you saying area when it's falling below the x-axis. I like to say that when the area is negative, it's just indicating that the function is below the x-axis. But really a definite integral is a limit of sums, and the application of those values can mean pretty much anything. So we have from 1 to 6. Well, there's a couple of parts here. We've got a rectangle, which we're going to simply find the area of by recognizing it as a common geometric region. And we also then, from the value of 3 to 6, need to recognize that we have to set up another integral. We have to set up and recognize the fact that starting at 3 and going to 6, we have another function that is defining the upper boundary of the area which we are trying to find, which means that we need a second integral. So the definite integral from 1 to 6 of g of x dx is actually equal to the definite integral from 1 to 3 of g of x dx, and then add that with the definite integral, hopefully you can see the difference between the blue and the green here, from 3 to 6 of, well, g of x dx. Now, I'm writing the same function name, but this function is a piecewise function and it's made up of different parts. So, for our first part here, from 1 to 3, we just have a common geometric region. We just have a rectangle, so it has a base of 2 and a height of 2. And then we're taking the definite integral from 3 to 6 of, where's it at? 2 times x minus 4 to the second power dx. Now, as you go to evaluate this definite integral without the aid of a calculator, then you have a couple of choices. You can simply take this binomial and expand it out. It does only have a power of 2, which is not that much. Doesn't take up that much time, but you're going to have 3 terms instead of just 2, and you're going to have 2 of those 3 terms be requesting the values of 6 and 3 as you plug in the lower and upper limits. So it really is a little bit quicker to evaluate this definite integral if we take this 2 and go ahead and move that constant out in front of the definite integral notation and recognize that inside of our power of 2, we've got a function of u. And then if we think of, say, on the side, saying let u equal x minus 4, well then du is simply equal to 1 dx. So if you think about that u substitution, you just need to have, since our derivative is a constant, that constant out here to finish up the chain rule. And the derivative of x minus 4 is just simply 1. And since I'm sort of introducing a multiplication of 1, you could say I'm balancing that with a division of 1. I'm just going to write this as a teaching purpose here for you. But for a very long time with integration, I would do straight u substitution, period, and never point out this completion of the chain rule. But I'm starting to realize with my years of experience that this AP test is timed, and, well, the more time you can save, maybe by just completing the chain rule or recognizing that it's already complete, you don't have to do a u substitution maybe to do some kind of integration. So we have 2 times 2 is 4, plus 2, and the integral of u to some power n, u prime, is u with that power increased, and then dividing by that increased power. And we're looking at here now with an upper limit of 6 and a lower limit of 3. I'm pausing though because I can see that I don't really want to write this 2/3 twice, again, as I think about saving time and being efficient with my work as I plug in the values of 6 and 3. So I'm going to go ahead and let that 2/3 move out and say that we have 4 plus 2/3 times x minus 4 cubed with that upper limit of 6 and 3 that we're about to plug in. So now we have 4 plus 2/3 times 6 minus 4 is equal to 2, and 2 cubed is 8. And then minus, plugging in the 3, 3 minus 4 is -1, and -1 cubed is -1. Now they're really kind of expecting you to make a sign error here. So you plug in the upper limit, minus, write that immediately, put a set of parentheses in, and then when you get -1 come out of your calculations again, you won't accidentally write just simply -1 when it really should be +1. So now we have 4 plus 2/3 times 9. Of course, 9 divided by 3 is 3, so we're looking at 4 plus 2 times 3, 4 plus 6. Well, that is equal to 10. Okay, let me double check my work here. Yes, we have a point for recognizing that you have a split at the x value of 3. So recognizing that this one definite integral really requires you to analyze 2 gives you a point. Writing the correct integrals with the proper limits is going to, not give you a point, but coming up with the correct antiderivative or integrating x minus 4 squared correctly gives you a point. And then finally, your final answer is going to give you that last third of the 3 points that you earned from this part. Let me go ahead and I need to erase this board a little bit. We'll get on to part C and D. No. Now for part C. For the open interval from -5 to 6, on what open intervals, if any, is the graph of f, which by the way we do not see, remember this is graph of g, the derivative, which has now been scribbled all over, where is f both increasing and concave up? Well, hopefully both of these parts are easy, but I think it's probably more obvious for you to identify where function f is increasing. Well, function f is going to be increasing wherever the derivative, in this case the graph of g, is positive, right? If your slope is positive, the function is increasing. So g was positive from 0 to 4 and from 4 to 6. But now we also want to know, combine that with, not only where is f increasing, but where is it concave up? Okay, well if I draw a function here, and let's just call this h, where is this function h concave up? It's concave up where it kind of creates an upward bowl, maybe somewhere from around here to here. Then there's a point of inflection, and it appears to be concave down. We teach a lot about when the second derivative is positive, the function's concave up, and when the second derivative is negative, then the original function, let's say h, if h double prime is greater than 0, then h is concave up, and when h double prime is negative, then h is concave down. Well, you really, if you want to answer these questions efficiently on the AP test, need to be able to talk about concavity in terms of the first derivative. If h double prime is greater than 0, positive, and h double prime is the slope of h prime, then h prime needs to be increasing. Well, maybe here h prime, the slope of h is -4. Now it's negative 3, -2, or maybe -1. Now it's 0, now it's 1, now it's 2. See, if it's concave up, then that slope is not necessarily positive or negative, but increasing. Negative, whatever I said, 4, -2, -1, 0, 1, and 2. The slope is changing from negative to positive, but it is always increasing. So see, saying that a second derivative is greater than 0 is saying that the first derivative is increasing. So where this graph of g, which has now been scribbled all over like I said, where this graph of g reading left to right is increasing, then f is concave up. So f is concave up between -2 and -1, but because these derivatives are negative, f is concave up but decreasing. Here's where we want to look at part C. Here we're getting answers from our derivative g or f prime, which are positive, but the derivative is also increasing. So, and I'm not going to write all of this out because of lack of room, but I'll say it nice and slow. F is both increasing and concave up on 0 to 1 because g, which is f prime, is positive. That takes care of the increasing part, and f prime is increasing. Thus, f is concave up. And this is just a constant positive slope. It's not really concave up or concave down. It's just some kind of linear section with a slope of 2. Then we have positive answers from our derivative, but the derivative is decreasing. Thus, f is concave down. And now let's say it, make sure we say this perfectly correct. From 4 to 6, f is both increasing and concave up on 4 to 6, and your justification will be because f prime or g is greater than 0 and f prime or g, whatever you're using, is increasing. Increasing is not the same as positive, and decreasing is not the same as negative. My students initially have a really hard time differentiating that. So that would be your answer. I verbally stated the justifications. We're looking at two intervals where the derivative f prime or g is greater than 0 and it is increasing. Now let's move on to part D, coming up right now. So for our last part here, we're going to find the x-coordinate of each point of inflection of the graph of f. Point of inflection. Well, the point of inflection for a function occurs where the second derivative changes sign. In terms of the first derivative then, the first derivative needs to change from increasing to decreasing or from decreasing to increasing, because if the first derivative is increasing, that means the second derivative is greater than 0. And if the first derivative is decreasing, the second derivative, the slope of the first derivative, will be negative. And it does not make any difference how the second derivative changes sign, like say from positive to negative or negative to positive, like it does when you discuss a justification for a first relative extrema using the first derivative test. So moving along left to right along our graph of f, which is also f prime, our first derivative is constant, it is increasing, it is constant, it is increasing, it is constant. So far, because we haven't changed from increasing to decreasing or from decreasing to increasing, we do not have an inflection point. But then our first derivative, f prime, say f prime or g, don't write the first derivative or the second derivative, use proper function identities, names. F prime or g starts to decrease and changes from decreasing to increasing at x equals 4. Thus, we have a point, the x-coordinate for the point of inflection is at the value of x minus 4. Now, I'm going to call off here and sign off for our video. I'm going to go ahead, though, and just show a written justification for C and D for maybe some foreign speaking or deaf students watching my lesson. I'm Mr. Tarrou. Bam! Go do your homework.